Okay, so hopefully you have had some time to read through the method, the student's method. So it is measure the initial length of the column of gas in the inverted test tube, leave the test tube in the beaker for a week, measure the final length of the column of gas in the test tube. Now, again, just to reiterate how important it is to understand the context that the question is giving yourself, putting yourself in. Essentially, there is some wet iron wool. There is a mixture of oxygen and neon gas in this inverted test tube. The word inverted means, as you can see from the diagram, it's a normal, ordinary test tube, but inverted means it's basically put upside down rather than the normal way we handle test tubes. Um, so the idea of this is to see, we know that the oxygen will react with the iron um, that is placed at the top, and therefore leaving behind only the neon gas, because we know neon is a noble gas. It is unreactive. So hopefully by the end of this 1 week, there should only be neon gas remaining within this test tube. No other gas can enter through because the water is blocking the path for that. Now, the question says some of the iron wool rusts. That is an indication of a chemical reaction taking place. It says give the chemical name for rust. Again, another recall question. We need to remember that this is iron oxide. You can say hydrated iron oxide. However, if you remember this formula, Fe2O3 for rust, that will give you the 1 mark, or just saying iron oxide is also absolutely fine as well. Iron oxide, we do need to put in Roman numerals the charge that the iron forms, and that is oxide. Either one of those will give you the mark. Give a reason why neon does not react with the iron wool. I've already just mentioned that. It is in group 0, which means, or group 8, which means it has neon. We can write has a full outer shell of electrons. Therefore, it is in its stable state. But it is only for 1 mark. That will give you the 1 mark. Part 3 of the question says the table shows the student's results. Use the results to calculate the percentage of oxygen in the mixture of oxygen and neon. Now, so whenever I see an initial and a final, straight away I need to calculate the difference. In order to work out the difference, I take the bigger numbers, which is 75. I subtract the smaller number from it, and I have 45 millimeters. Okay, so if I have 45 millimeters, that is the difference. That is 45 millimeters less in terms of the length of column of gas. I can then use that 45 millimeters um, as the volume, or as the amount, in a way, of how much oxygen that has been used, that has been reacted. I then divide the 45 millimeters by 75, which was the total. So I take the what has been used, what is the oxygen, and then I do what is the total, and this will give me. I'm just going to put that in a calculator to see what that gives me. So I am using my computer's calculator, just opening up. Of course, make sure, as we said at the beginning of the video, that we need to have our calculators at hand. You do need a calculator and a ruler. Um, so 45 divided by 75, it is 0.6. There we go, got that out the way. Now, in order to turn this into a percentage, I know I can very nicely turn this into a percentage just by multiplying the 0.6 by 100. This gives me a total of 60%. Do remember to write your answer in the answer line so the examiner is not looking for your answers. That's 60%. That gives you a nice little 2 marks as well. Brilliant. The next question, question 4. A student uses this apparatus to investigate um, the dyes in a food coloring A. So um, I can see some sort of a chromatography setup. Look at the diagram. Now read the question as well. It says, explain two mistakes that the student makes when setting up the apparatus. Okay, excellent. Let me have a look at the labels. What has the student actually done? Already, I can see this might be the water, um, up to where the water is. And remembering from class experiments that that baseline, it needs to be above the water line. Okay, so the baseline, but also that dot as well. If it's submerged in the water, we know that, particularly if the baseline is drawn in ink, that's the second mistake. It will interfere with the results, and the sample just may dissolve within the water, within the solvent. So, mistake number one, we can say water level is above the baseline, and then it is 4 marks, so we need to identify two mistakes and then explain each of the mistakes. And the explanation for this will be, um, will the um, sample will mix or dissolve, you can write dissolve, um, in the water, giving you inaccurate results. Mistake number two, I can, of course, write the second mistake here, but just where the question has already written number two, write the second one, follow the guidance. I know I've got two extra lines of space, but just following the guidance, it makes it a lot clearer for the examiner when they are marking your work. So, baseline drawn in ink. Again, that is a mistake. So will interfere. This will interfere. Use this word. This is a key word. Interfere with the results. Okay. So there we go. And that is a nice, easy 4 marks there from chromatography. This question is about the student repeats the experiment but with no mistakes. The table shows the RF values for the two dyes in the coloring in food coloring A. Blue dye, yellow dye, 0.5. Okay. Complete the chromatogram for food coloring A by adding and labeling the dyes. Okay, excellent. So um, now completing the chromatogram, we are expected to identify where roughly the dots will be. In order to do that, we need to kind of measure how the height of the paper, the height of the waterfront, and approximately um, where would the dots have reached? How far would they have traveled? Now, because we've got the RF values, we can find that out. We can find that out by looking at the equation for the RF values. I know this is not your ordinary method of seeing chromatography questions, but this is nice because it gets you to think a little bit outside the box. Now, the formula for RF values, it is distance moved by, I'm just going to put dye to make it easier, divided by distance moved by solvent front. Leave that as solvent. Now, if that equals RF, so I'm going to just do the blue one here. Let's get the blue one out of the way first. So the blue one, RF is 0.5. If this equals something divided by distance moved by the die, so where the spot is, divided by, I'm going to quickly take a ruler and measure the height of this. And essentially, that should be, I'm just going to make up some numbers right now too. If I do measure, I'm going to say this is about 10 centimeters where the solvent front is. So I'm going to put 10 at the base here, and the top distance moved by the die, I'm going to leave a question mark. Um, if I rearrange this equation to find what that question mark is, basically 0.5, 0, I'm going to multiply both sides by 10 times by 10. This should give me what the question mark is. It's an easy calculation. I can do it in my head. That is 5 is equal to the distance moved by the solver, by the die. So take my ruler again, just measure 5 centimeters, although this looks a lot, um, not like 10, but anyway, about halfway through that paper, that I'm going to mark that as my point A, sorry, point blue. That's going to be my blue die. And then for the second one, I'm going to do the yellow over on this side. So that's 0.25 is equal to, and then again, basically, I'm just going to put distance, D for distance, and then die, distance the die moved, just to make things a little bit easier for myself. Divide that by distance moved by the solvent, which is still going to be 10. It needs to be the exact same thing. They were in the same solvent. Again, rearrange this and multiply both sides by 10. Distance moved by die. But in this case, the yellow die. So 0.25 times that is, this should be about, so just going 2.5, yeah, essentially 2.5 centimeters in this case, which should be approximately about a quarter of the way. There we go. And that should be roughly about the quarter of the way to the top. And this one I'm going to label as yellow. Okay, that will give me the 2 marks over there. There is another way to do this without doing all of these calculations. Is when you get used to the RF values, you need to know that, okay, wherever you see a zero point 0.5, that is halfway, and 0.25, that is a quarter of the way up, because 1 or 100% of the way, that will be all the way to the top. Okay. Now, part two of the question says, give a reason why the blue die has a larger RF value than the yellow die. So here you can write down, of course, because it has moved further up, um, you can write blue dye has better solubility. It has better solubility in the solvent. So the better um, it dissolves, the higher it will travel with the solvent, and that's a nice little one mark. Or of course you can write the other way around. Yellow dye has a worse solubility for the solvent in the solvent. Question 5. A student investigates the reactivities of four metals: aluminium, magnesium, copper, and metal X. The student adds pieces of magnesium ribbon to aqueous solutions of the sulfates of each metal. After a few minutes, the student removes the pieces of magnesium ribbon and records the appearance of each piece of magnesium. Table 1 shows the student's results. Okay, that's the results. Now, part one says, name the substance that causes the brown coating on the magnesium. Just quickly have a look at this table of results. I see the brown coating. There we go. I've spotted the brown coating. Now, that is when magnesium ribbon um, has been put in in a solution of copper sulfate. Now that clearly tells me that the copper there has been a reaction called these displacement reaction. The copper has now formed, and the magnesium has gone into the solution, or at least on the surface of the magnesium ribbon. Now you need to recall the displacement reactions and why we have them. Of course, the one that displaces the other metal, it means that that is more reactive. In this substance, I know magnesium is more reactive or higher in the reactivity than the copper, which is why the magnesium will displace the copper in the solution. So the brown coating must therefore be pure copper that forms on the magnesium ribbon. The substance with the brown coating, so for this one, which should be copper. And then part two of the question says, state why there is no change with magnesium sulfate solution. We just explained it. However, this time round, magnesium will not displace magnesium. And essentially, that's what you're right. So magnesium will not displace magnesium because they are, of course, the same thing. Now, next question. Same question, part B. The student repeats the experiment with pieces of metal X instead of pieces of magnesium. And there we go. We've got another table of results. Use the information from both tables to deduce the order of reactivity of aluminium, magnesium, copper, and metal X. Um, so, wherever we see no change, so on these three, it tells me that the metal in the solution is more reactive than what it's been reacting with. Okay, so this is all metal X. Of course, I'm going to see no reaction here because the metal will not displace itself, like the previous question we just said. With copper, I do see that metal X was able to displace copper. So I'm going to go ahead and put copper as the least reactive. And Okay, so with magnesium and aluminium, I can see that they are both no change, which means metal X is actually less reactive than magnesium and aluminium. I'm going to put metal X here as the third one. And then between magnesium and aluminium, I just quickly flip back to the other table. And I remember this was magnesium reacting with aluminium sulfate, and there was a reaction. There was a sign of a reaction. We had a grey coating on magnesium, the aluminium, so it did displace it, which tells me the order of reactivity. The most reactive being magnesium, and then aluminium. You can go ahead and memorize this order of reactivity. You know, the order of reactivity that we have looked at within lessons and within classes, they do not change. I do highly doubt exam questions will give you a false information there or try to catch you out. Now, here it says give a possible identity for metal X. Again, if you've remembered this, you would have remembered that metal X could either be iron or it could either be zinc. So those are the five metals that we normally look at, five or six metals in terms of their reactivity. So you can either put iron here or you can also put zinc. Those are the two metals that are missing from our reactivity series. Part C of this question says this ionic equation represents a reaction between magnesium and aluminium nitrate. Explain in terms of electrons which species acts as a reducing agent. Now, let's just underline that. A reducing agent itself means that the thing that it is reacting with. So we're essentially looking between these two because one of them reduces the other one. Now, just very quickly, we can put our little oil rig to help us remember what reducing and oxidation means. So oxidation is loss, reduction is gain. These little mnemonics, they do help you. They save your life. I still use them. Um, so reduction is gain. So we're looking at the species that has gained electrons. Now, magnesium, to start off with, this is in its um, solid, so it's in its atomic charge, so no charge really there. And then it goes on to become a +2 charge. I see that. So from 0 to +2, whereas aluminium goes from a 3 plus 2, let's just put 3 plus, it goes to 0 in its elemental form. Now, the one that has gained the electrons, it should go from a higher charge to, it should go, okay, gaining electrons, remembering that electrons are negative. So from a higher charge to a lower charge. Magnesium has gone from a 0 to a +2, which means it has lost electrons. Aluminium has gone from a +3 to a 0. So the species that has got reduced is the aluminium because it has gained electrons. Okay. So therefore, the reducing agent, what made this aluminium gained those three electrons must have been what it was reacting with. So here it was the magnesium. Now the answer would be reducing agent. You can write it like this for 2 marks. So I'd say 1 mark to identify the reducing agent is magnesium. You can even just put Mg. That's also fine. And then the explanation: um, magnesium. Uh, we can say donated electrons to, in fact, let's just put Al3 plus. It makes it faster to write, and that will give you the mark for that. Okay, so magnesium donated electrons to that. Therefore, I like to use these three dots as therefore. Aluminium got reduced or gained electrons. Now, next question. I'm just having a look at the time. Question 6. Okay. On realizing the time, I've got about 9 more minutes of this video, and wherever I reach, I'm going to upload this onto YouTube so you can watch it quickly, and then just um, so you have an idea of how to do exam questions. This question is about polymers. This is the structure of a monomer. We've done this in class recently. What is the name of this monomer? So you look at the, just write these, always write these. Prop Butte Pent Hex, right? Because I mean, even in this question, if for example you only have two carbons, so this is 1, 2, 3, 4, 5, and 6. So you might need them for later questions. It is good to just note down the basic of your organic chemistry. Two carbons, so the name must start with an S, the suffix. There is a double bond, so I know this must be an alkene, and also I see a halogen attached to it as well. So this must be a chloroethene. I'll just write chloroethene. I look at the options that it gives me, and there we go. The correct answer corresponds with option B. Complete the equation to show the repeat unit of the polymer that forms from this monomer. So remember that bond, double bond breaks, giving one bond on either side. Remember that bond has to cross the square brackets for you to get those marks. And then the two hydrogens, they stay where they are on that carbon. And the chlorine goes there, the hydrogen goes beneath, like that. The N has already been done for us as well. Fantastic. So a typical molecule of the polymer has a relative mass of approximately 2.5 million. Show that the number of the monomer molecules needed to make this typical molecule is about 40,000. Okay. In order to do that, let's work out the um, uh, relative molecular mass for one of the monomer. So we don't even need a periodic table for this one. I know it's giving us the atomic mass, relative atomic masses for carbon and chlorine. These are the ones that we should be using. There are two carbons there, so let's do 2 multiplied by 12, and let's add 1 multiplied by, there's only one chlorine, 35.5. And we're going to add how many hydrogen? 3 hydrogens. So 3 times by 1. Then let's just sum it all up. That's 24 plus 35.5 plus 3. This gives me a total sum of, um, I'm doing this in my head, so 24, 35, 39. 59.5, 59.5, that gives me 62.5. And in your calculators, of course, do use your calculators. If this is the relative formula for one monomer, you basically take the whole thing, 2490000 divided by the relative formula mass for one of them, and this gives you approximately, should give you approximately 40,000 um, units, and then that will give you the 2 marks there. It might give you something like 38,000 or 39,000, but there we go. Um, these are two methods used to dispose of the polymer: burying in landfill site or burning. Discuss the environmental problems caused by these two methods of disposal. 4 marks. So I would separate 2 marks for each of these bullet points that it gives me. Now, burying in landfill sites. So problem number one is um, takes takes a very long time to break down. Takes a very, and you can, this is the only place that you can exaggerate and use the word very, long time to break down, which means basically it will remain on the landfill site almost forever. And therefore it just takes up land. If it stays in the land for a long time, it will just take up landfill space. There's and what the other issue is. So it takes a long time to break. It basically takes up space. That could be 2 marks there. And then 2 marks for burning. Of course, as burning with any hydrocarbon releases CO2, which is you can greenhouse gas, so bad for the environment. And another point could be that particularly this one, it's got chlorine in there as well. So chlorine released, and that's never going to be good for the environment. We could end up we could end up with hydrochloric acid either in the atmosphere, and we know hydrochloric acid, it is a strong acid, and the damages that it can do is quite severe. So if you word it, but as long as you mention these points, you'll get the 4 marks over there. 4 different points. A different polymer molecule contains 10,600 atoms of carbon, 10,600 atoms of hydrogen, and 31,800 atoms of chlorine. Determine the empirical formula of this polymer. So this goes again to our empirical formula. However, this is just a simple ratio. So 10,600 to 10,600 to 31,800. Um, Different ways we can go about this. One of them is just look at the what we are looking for is the highest common factor, or what we are looking for is basically the highest multiple that goes in all of them. So 10,600, 10,000. I mean, I can divide all of these by 10,600. If I were to divide, I'm just going to put it on my calculator, 31,800, just to see if 10,600 goes into it, divided by 10,600. This gives me 3. Perfect. So it does go into it. 10,600 divided by 10,600 divided by 10,600. Divide this by 10,600. The ratio, this gives me 1 to 1 to 3. And therefore, I know that the empirical formula should be 1 carbon to 1 hydrogen to 3 chlorines. That's an L and a little 3. Let me get rid of that. So the empirical formula, I'll write it clearly here. CHCl3, and that's for 2 marks. So do have a go at answering these questions. All the very best wishes for now. I will upload the remainder questions with time.